Hi everybody, we just have seen the finite automata as a graphic representation, and then remember that, and then we're going to see that the finite automata, it can be also represented as an algorithm. Any finite automata can be interpreted as an algorithm in pseudocode. For example, we have the algorithm called finite automata. This is the variable declaration, C as a symbol, S as state, and we have S is the initial state. So we loop like there are symbols. While there are symbols to read, we haven't arrived to the final state. Do the C read the symbol, while we are here, while we haven't arrived to D, C read the symbol, and S determine the new state. How? With the actual state and the symbol just read. You see that there is S and S, so this is a recurrent function, and when it's done, there is a condition. If the final state A, then write word accept. So if the algorithm has arrived to D, then the word is accept, else the word is reject. The quantity of memory needed by finite automata is independent to the length of the string. It's language that need algorithms which use a quantity of memory relative to the length of the string are not finite automata. Then, new topic. Formal definition of a DFA. The automata with a finite number of states, only one initial state, and for every symbol only one transition, are called deterministic finite automata, or DFA, like we have been seeing. To define a DFA must be known the set of states, the initial state, the acceptors states, or final states, the word alphabet, and how to determine a new state according to symbol read and the present state. A DFA is a tuple with the following form, where Q is the set of final state, sigma is the alphabet, QO is the initial state, F is the set of acceptors of final states, and this is the transition function. So the transition function, given state and a symbol, finds a state. For example, this is the last automata we have seen, and then how to find all this information, all information of the tuple that defines the automata. This is called A. Q is the number of states, is the name of the state, sorry. A, B, C, and D. Sigma is the language. Language is A and B, the words, the symbols, sorry, symbols, A and B. Q Q0 is the initial state, A. Remember, the arrow is the starting point. The final state is D, because it has two circles. And this is the transition function. So, transition function tells us, given a state and an input symbol, where we have to go. So we are in A starting point. Given an A starting point, state A, given an A, we go to B. We go to B. A, given an A, go to B. If we have as input a B, we go to C. We go to C. And the same is equal. If we are in B and we get an A, we remain in B. B, B. If we get a B, we go to D. We go to D. Well, the same. Thanks to the finite number of states and symbols of sigma, the transition function can be defined in a table like this. And to finish the video, you are going to see the formal definition of a language recognized or accepted by a DFA. To define what is understood by a language accepted by an automata, we define a new transition function. This new transition function, what tells us is that given a state and a symbol, we are always to find a new state for every symbol in a state. This is what is meant here, only that if the word is empty, we remain. If we get an empty word, we remain in the same state. This function is called extended transition function. So when a state and a word is given, the result is another state. With a DFA A like this, the language accepted by A is called LA, is defined as the language accepted by A are the words, symbols, belongs to the alphabet, and the transition function always find the final state. So in natural language, LA is just the word set that from the initial state arrives to the final state. So it's the set of all words that begins with A and finish in D. That's all for this video. See you.